All right. Hello, everyone. This is Volts for June 11th, 2025. Making electric motors better. I'm your host, David Roberts. Here on Volts, we have covered all sorts of electrical devices and technologies, from solar panels to batteries, appliances, and EVs. But there is one technology at the very heart of the electricity system that receives strangely little attention from those of us in the clean energy space. I am talking about the humble motor. Electric motors are found everywhere, from scooters and leaf blowers to HVAC equipment, water pumps, cars, planes. Something like 50% of the world's electricity flows through them. And if we're going to complete the energy transition, then everything that now runs on a fossil-fueled engine will eventually have to run on an electric motor. Yet, I have given motors scarcely a passing thought over the years and have seen very little discussion of the subject in clean energy circles. It's been nagging me for the last year or two, and I've been waiting for the right opportunity. So I was pleased when the folks from Conifer got in touch. Conifer, which just received its first $20 million in seed funding, is designing electric motors and drivetrains that are lighter, more efficient, more cheaply manufactured, and made without rare earth magnets. Or so they say. I'm going to talk with co-founder Ankit Somani today about how to improve motors and what the future holds for them. All right, then, with no further ado, Ankit Somani, welcome to Volts. Thank you so much for coming.
Thank you, David. It's great to be here.
Let's talk about how you ended up here. So you're a what they call a serial entrepreneur. You've had your hands in a lot of different clean energy businesses over the years. So you look around for your next big thing. Why motors? Why motors and powertrains? What's the logic that brought you here?
Just like for most folks, my career has been long and windy as well. I actually first came to the US in about, I think, 2007, right in the middle of the financial crisis, to do a master's in data center cooling. Yeah, as you can imagine, it's a hot topic now.
Very prescient. Yeah, well, good call. It was a good call.
So it was a long time ago, but had a really good program around that, and then spent years in Oracle and Google designing different cooling and electrical equipment for data centers. It was a very focused R&D team. So had early background around motors and different aspects of it back then, but then forgot all about it for the longest time. So the first startup I did, that was in conversational AI, very different space. We had a good opportunity to scale and then eventually sell that company. And then I reconnected with an old friend of mine from undergraduate who has been living and breathing motors since third year college. So he did his PhD in electric motors, had recently designed electric powertrains for Apple's secret car project and then for Lucid.
Oh, right.
Yeah, so lots of deep background there. And we started chatting about the problems across the board in motors, all the way from how we choose the supply chain for it, what sort of manufacturing processes exist today, what are challenges from a design and performance standpoint. And the biggest takeaway we had was, if we really want to see a lot more electrification and physical automation, we are sort of stuck in the 5 to 10% penetration in that world. And if we really want to see something which goes way above 50% penetration, then you have to think about the electric engine from the ground up. I use the word engine because, just like fuel tanks, battery is an energy store, but you got to take that and convert it into a spinning wheel or a spinning fan on the other side. So everything in the middle is the engine itself. And you have to think about it ground up across all of these three areas. We had a few innovations in mind, and one thing led to another, and here we are.
I suspect lots of listeners are roughly like me in this area, which is floundering in near total ignorance of physical engineering. So you'll have to be patient with me as we walk through this. But just so a motor is part of a powertrain, which consists of the motor, there's an inverter, a gearbox, and some sort of control software. If you add all those up together, is that sort of the equivalent of a fossil-fueled engine? Like a fossil-fueled engine has all those bits in it?
That's exactly right. You described it perfectly.
So powertrain is like the electric equivalent of engine, basically.
Correct.
And you are at Conifer working on motors, but also, as I understand it, working on inverters and gearboxes and control software, the whole package.
That's right. Yeah, we are a verticalized electric powertrain company. And not only on each of these 3 or 4 aspects that you mentioned, which is motor, inverter, gearbox, control software, but also we have experts internally reinventing the manufacturing process and automating it.
So is it your experience, like, am I right that this is an odd sort of lacuna in, there's so much activity around clean energy these days, so much excitement, so many startups, it's buzzing. I'm not wrong, right? That it's a little weird that the heart of all this, the engine, the drivetrains at the heart of all this, have had very little attention paid to them by all this wave of entrepreneurs. Like, is there activity in this area that I've just been missing, or am I right that like it's been neglected?
No, you're absolutely right. And that was actually an observation we also had, what you arrived at about 2.5 years ago, where if you look at the battery world, in the last 15 years, there's been so much investment, so much good talent that has gone in there, so much focus, and around the world, like all the way from battery chemistry to the anode to the cathode to the manufacturing process, recycling.
The whole process.
Exactly. Every different aspect of it. So batteries got maybe 1,000 times more venture capital and maybe 1,000,000 times more attention from folks. And electric motors, the humble electric motor that has served us over 100 years, people had forgotten about it, that, hey, we think it's a one and done problem, but there's so much to it that was worth solving.
So as I understand it, and tell me if I'm right about this, Conifer has sort of 3 big innovations that I would like to walk through one at a time. The first is you're making an axial flux motor rather than a radial flux motor.
Mm-hmm.
We'll get to what that means. The second is you are using iron-based magnets rather than rare earth-based magnets, which has big supply chain implications that we'll get to. And the third is these innovations in the manufacturing process, basically making it easier and cheaper to manufacture these things. Are those roughly the big 3? Is that roughly the menu here?
Yep, that's very close to it. And within the axial flux itself, we have reinvented the core stator itself, which essentially enables all these 3 things and makes it possible.
Got it. Okay, so let's start with, I spent a couple of nights ago, several hours falling down a YouTube rabbit hole about radial versus axial flux motors. Turns out there's a lot of material out there, a lot of strong feelings, oddly strong feelings about these engineering decisions. So if I can just describe this very basically, and tell me if this is correct. There's 2 basic parts to the electric motor. There's the stator, which is the static component that contains the copper coils. And then there's the rotor, which is the moving component that basically is moving magnets past the copper coils. And that's what generates the electricity, is moving magnets past electric coils. So in a radial flux motor, the stator, the static bit, is like a cylindrical tube, and the rotor is like inserted into that tube. It's like a little cylinder inside a bigger cylinder. That's what radial means. That has to do with the angle of the magnetic field toward the magnets, but I don't know that we need to really get into that. Axial flux is, rather than a tube inserted in another tube, it's like 2 discs next to each other. like think of like dinner plates or something, right next to each other. One is the stator containing the coils, one is the rotor containing the magnets, and the one spins next to the other one. That's an axial flux motor. Is that roughly correct?
Very good. I feel like within 2 days itself, you almost become an expert across all of these things. By the way, I'll add a fun fact. Nikola Tesla's first patent on electric motors, this is back in late 1800s.
Yeah.
That was for an axial flux motor.
Interesting.
And even though 95% or even higher motors in the world today are radial flux motors, because that's where both manufacturability as well as innovations were over the last century. That was initial.
Yeah, can we explain that a little bit better? Why did radial, like as you say, something like 95% of the electric motors around us today are radial flux motors. Is there an easy to understand reason why they came to be so dominant?
Yeah, actually, when electric motors first started, they didn't even necessarily have magnets in them. So your rotor was excited. So you basically created an artificial magnet by rotors also having copper coils and current go through them.
Interesting.
And just the connection itself is much simpler when you do that in a radial flux configuration. So it's easier to get started that way. And then, as you know, these things are always incremental. So people build on top of each other. And once forgotten architecture, now with the right permanent magnets or the right coil winding, actually has much better advantages than the typical radial flux motor.
Yeah. As I understand it, you get a bunch of advantages from going axial flux instead of radial flux. But as I understand it, the thing that's tricky about it is just that it's a little bit more precise and a little bit more difficult to manufacture. That's why there's not been a larger move in that direction. And you guys presumably are tackling that problem. Tell us quickly then, what are the advantages of axial flux over radial flux?
In an axial flux motor, or actually any motor, the way you determine how much force that motor is able to generate, which, in motor parlance, it's called torque. Torque is essentially force over a distance. In a radial flux motor, what happens is your cylinder, as you were talking about, that is inserted in the spinning cylinder, which is inserted in the static cylinder, that's at a much lower radius. And so the force that you have to produce is a lot more so that your torque is still similar because your distance is small, because it's a small cylinder, small radius cylinder.
So it's just as simple as like the spinning part on an axial flux motor is larger. It has a larger radius, and thus it's sort of, swinging around a larger perimeter.
Yeah, think of it as the force generating part, which is where the magnet is right next to. It's called the air gap in that parlance, but where the magnet is right next to the stator coils itself, that's much further out in an axial flux system. So now if you can make it further out, but also at the same time generate higher magnetic field as well as spin it faster, then you can generate a lot more torque as well as power from the same amount of material compared to a radial flux system.
So the basic and perhaps most key advantage here is that you can make them smaller. You can get more torque out of the same amount of material, or alternatively, an equal amount of torque out of a smaller motor.
Correct. And the term that's used very often is power or torque density, which technically is power produced over a volume of space that you occupy. But even as power over weight, like kilograms or pounds, even that can be much higher in an axial flux system.
Mm-hmm. And as you said, this is not you guys did not invent axial flux motors. They've been around for centuries, and they're even around a lot today. So have you, how is your sort of torque per volume relative to other axial flux motors? Like, are you pushing the boundaries on that particular metric?
Yeah, absolutely. So there were changes we made in the stator itself, which allowed us to compact a lot more electrical conductors in the same space.
coils, right? Those are the
Coils.
copper coils, right?
That's right. And that's the principle of electromagnetism that motor is based on, because a current carrying conductor produces a magnetic field around it. So now if you can, just in the layman terms, if you can have a lot more conductor in the same space while effectively being able to cool them because they run hot as well.
Yes, this is something I ran into as a problem, the heat, dissipating that heat. So you've crammed in more copper coils and figured out some way to disperse the heat from them.
That's right. And cramming doing two different things. One, it generates a much stronger magnetic field, but at the same time, cramming it in a way such that the manufacturing process, in fact, becomes much simpler than a typical radial flux system. So not only we've made axial flux feasible, more feasible rather at scale, but it has become a tenth simpler than a typical radial flux system in terms of winding that coil.
In here, you're just referring literally to the physical manufacturing process of getting the coils into the stator and completing the stator. That process, you've made it easier.
That's right. Making the coil, making sure it's in the right place in the stator, and making sure we can do it with the least amount of or least complicated manufacturing process that we have invented.
Right. So you can make these smaller. You can get the same amount of torque out of a smaller motor. So that, I think, explains your business plan, which is starting basically with small motors. The second innovation is in the magnets. Typical electric motors use magnets that are made out of rare earths. Neodymium, did I say that right?
Yes, you got it.
Is the main one, I think, and there's, I think, are a couple of others involved. And of course, listeners to Volts know that China completely dominates the mining and even more particularly the processing of rare earth minerals. So insofar as all electric devices require motors and all electric motors require rare earths, like China has, power over not just our electrical grid. I mean, they have some trade power over, our lawnmowers and cars and everything else that has an engine in it. So there are economic and national security reasons to move away from rare earths, long story short. So how did you do this? Because my understanding is that the reason you use rare earth magnets is that they are particularly potent, powerful. You're replacing them with ferrite, which is, as I understand it, basically iron. So how are you compensating for that loss of power?
Yeah. By the way, ferrite magnets is 86% rust. So it is literally ferrous oxide, 86% rust. And these are the same magnets that you would find in your, the kitchen fridge stickies that you have, which sticks well on your kitchen fridge. Those are the ferrite magnets. It's the same. So there are two key challenges that had to be solved. First, as I was talking about earlier, if you can generate higher magnetic flux from your coils, which we talked about from our stator technology, then you can pair it with a weaker magnet.
Right.
So that is the first innovation, and that helps from a torque standpoint. Now, a very simple, like the way you think about power, in a typical world, it's force times velocity. And in the motor world, it tends to be torque times how fast you can spin it. So if you have to increase power density now, if you've gotten torque to a good point, now you have to spin the motor faster to be able to do that. So one of the challenges you have with ferrite material is it's like ceramic material. If you've ever had something ceramic and it has slipped out of your hands, you see it breaking very quickly.
Yeah, brittle.
It's the same problem, with ferrite magnets. So we figured out how to structurally save it when you spin it at much, much higher speeds, structurally strengthen it.
So it literally just holds together at higher speeds.
It holds together much better at higher speeds, make sure the integrity is good. So it was partly because we had a better stator and partly because we figured out structural challenges that we could have solved from a ferrite standpoint. That's what allows us to use a weaker magnet. It's not just a weaker magnet, by the way, it's much, much more cost effective. like compared to rare earth magnets.
I mean, iron is, abundant, let's say.
Yeah,
Not expensive.
it's less than half the cost of copper itself per pound. It's that cheap.
And very easy to get anywhere. You don't need a foreign supply chain. So by getting more out of your coils and by spinning faster, you've basically compensated for moving from a stronger magnet to a weaker one. And so this is allowing you to use much cheaper magnets and magnets that don't require foreign supply chains, basically.
That's right.
Before we get to the manufacturing part, let's just talk about what you're going to do with this new motor you've got. What is the sort of first step on the business plan?
One statistic that blew our minds when we started looking into it more deeply is that there are 1 billion small gas engines that exist in the world.
I know, and they're the dirtiest per weight, per unit. The dirtiest fossil fuel technologies, almost these little like scooters and leaf blowers and all those little things.
Exactly. In fact, California has a very interesting acronym for it. It's called SOAR. They're literally SOAR, small off-road gas engines. And you're right. They're dirty in terms of SOx and NOx emissions. While the world focused on cars and trucks, we sort of forgot about making these better. And just for reference, by the way, when I say 1 billion gas engines, they are about 1.4 billion cars. So it's roughly in the same order of magnitude what exists in the world. And so that's the market we want to target because it's oft forgotten, but extremely important from an electrification standpoint.
So where are those motors, like those billion motors, presumably are clustered in a few big product categories? Where are they?
There's so many different applications. I'll name a few. There's two-wheelers, small delivery vehicles, three-wheelers. You have all sorts of power tools and equipment. If you've used, pressure washer, you'd see it in that. If you'd use a commercial lawnmower, you'll see it in that. You have agricultural equipment. Almost all agricultural equipment have that. So it's really spread across many, many different applications. And the thing we wanted to solve is with a few different SKUs, can you address most of these applications? Because then you can create something standardized. Like let's say you go to a place that sells you gas engines. You can say, oh, I need a Honda 5 horsepower gas engine. And they'll give you a standardized unit that comes out. So what's the equivalent of that that we can produce, which people can just deploy?
So that engine can go in a number of different applications.
That's right.
And so similarly, you're trying to make a motor that can sort of like work in all these different applications.
Absolutely. And this is a big part of our story, but it's only part of our story. There's a whole set of stationary applications, which are, we were talking about data centers earlier, but all sorts of fans, pumps, all the physical industrial automation.
Yeah, talk about things people don't think about.
Exactly.
We're surrounded by those, and they're practically invisible.
There's a reason why 50% of world's energy goes through these motors. They are everywhere.
Yeah. So when I started reading about water pumps, I was like, wow, it is wild. You really are surrounded by those.
Correct.
And so, like we have electric motors now. You can get an electric leaf blower.
Mm-hmm.
So does your little motor outperform whatever little motors are in today's leaf blowers? What are those motors in today's leaf blowers? What's wrong with the sort of, why aren't they spreading faster? What's wrong with today's small electric motors?
Very good question. So there are 2 or 3 factors that really will matter for us to go from, as we were talking about earlier, the 10% or so electrification to 50, 60, 70% electrification. First is, do they do the job in a way that consumers like, which means low noise. If you think about leaf blowers, I don't want to carry like something 10, 20 pounds in my hand all the time. Like, are they light at the end of the day? Are they cheap enough? Because the next set of consumers, they don't think about being green. They just think about, is it affordable, reliable? Is it more cost effective? That's what they care about. So it's those factors that you need to push on. And now with rare earth material coming more in spotlight, you need to solve for supply chain issues. Like one of the biggest things we see recently is customers coming to us and saying, hey, we are not able to get enough of them. And is like long lead times associated with it because there are some critical parts coming from very supply chain constrained global places. So it's across all of these factors that you can make an improvement.
One of the things you boast about your stator is that it's much lighter. Like your whole motor is lighter than existing motors. How is that? Where are you saving the mass?
So a very common material that is used in electric motors is called silicon steel. Mm-hmm. And we have eliminated 95% of silicon steel from our stators itself. We also use 20% lesser copper at the same time. By the way, the reduction in steel is not just in the actual material itself, but the way steel is put into these motors, there's a lot of scrap material generated. And we've innovated on that, where in our case, the amount of scrap that is generated is very, very low. So it's also a much simpler process.
Did you substitute some material in particular for the steel?
No, so there's no like switch and bait. There's no like, oh, we're not talking about some fancy material that we are using that others don't. It is simply the right manufacturing process coupled with the right design. And then that allows us to also use other simpler materials like the rare earth free magnets, which is iron magnets on top of it.
Right.
So we need to take inspiration from how IC engines were made, where there was simple materials, simple process made across the world. That's how electric motors and electric engines need to be, not like complicated materials or complicated processes. It needs to be as simple as IC engines for it to be prolific.
So your first two products, just to get back to the business plan here real quickly, the first two products are a motor that is sort of freestanding and can go in pumps and stuff like that. And then what I found very interesting is this in-wheel motor that you're making. Well, that I guess is technically a drivetrain, because in the wheel you have the motor and the gearbox and the everything. So talk a little bit about your innovations outside the motor, in the inverter and gearbox and control software and stuff like that. Like, are you also pushing ahead on those?
Yeah, absolutely. So our core product, the product that we started with, is an in-wheel solution. And our vision there is you actually should not be putting motors in the chassis itself as much as possible.
And that's up to what size? What's the limit on that? You mean even like cars, big trucks?
I absolutely believe that cars and trucks are going in the direction of not requiring motors inside the chassis. It'll be all in the wheels.
And this is something like I read a very sort of excitable, futuristic, etc. book about electric vehicles way back in it was like 2007 or something. And one of the things that the engineers were most excited about were these in-wheel motors, because that just frees up the design space. Like design-wise, it's incredible. It just completely opens a blank slate everywhere else, right? Like you can put any platform, any structure, any kind of vehicle. Like if you have the motor in the wheel, you can build anything on top of those. Like the sky's the limit.
Yeah, exactly. And imagine as simple as I'm going to take this wheel, I'm going to connect this with this chassis, and boom, I have a new kind of platform that I can work with versus custom designing for each vehicle.
Right.
And as you're absolutely right, it's been the dream for electric vehicle makers for the longest time to have a solution like that. So we are big believers, very long on that. And that required innovation, not just in the motor, which is very compact for us. And we have this modularity element too, like we can have a single motor or a tandem motor or three motors like in the same packaging. Very easily.
Right, because the axial flux motors, as I said earlier, are like discs next to each other. So it's really just like stacking discs.
The world thinks of them as pancake motors. That is the form factor. And so now we have connected that with a special gearbox that we made internally, which is also very pancakey. And together, with both of them together, the system just disappears inside the wheel. And so nothing sort of jets out. and delivers amazing power density. So that's on the gearbox itself, the changes that we had to make.
And I'm just curious, this in-wheel motor, like, because when I think about wheels, there's there's a lot of different kind of wheels. There's a lot of different kind of vehicles, a lot of different sizes, a lot of different, weights on top of them, et cetera. Sort of how agnostic is this in-wheel motor? Is it the same basic thing that goes in all these different kinds of wheels, or do you have to do like a different design per wheel category? You know what I mean?
Yeah, this was a key decision for us and a key value proposition of what we are doing. So typically what happens is there've been these products that have existed in the market called hub motors.
Right.
Now, hub motors live inside the wheel as well, but they tend to spin with the wheel. And every time you change the size or shape of the wheel, you have to basically use a different kind of hub motor. So that's your least scalable option.
Got it.
What we are doing is something that is in wheel, but is decoupled from the wheel. So you can basically take the same motor and gearbox and you can put it on a 12-inch wheel, on a 10-inch wheel, on a 16-inch wheel, and you can deliver different performance. So we are able to get to a wide variety of applications with just 2 or 3 SKUs on the motor and gearbox side.
Interesting. So I'm assuming that like the motor that's going to work, across like, I don't know, a 2-wheeler, a 3-wheeler is not also going to work in a car. You know what I mean? Like presumably you do have a bigger version of this.
That's right.
But are you currently able to make one that could run an actual car, or are you working up to that? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who change majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Are you currently able to make one that could run an actual car, or are you working up to that?
Yeah, we have some interesting small car customers as well. So we obviously have to focus in one area, and it's a way from a business standpoint, we just need to be more focused.
Yeah.
But we have gotten interest and have checked out feasibility across a bunch of different applications. And you're right, it's not going to be the same motor across all of it, but within 1 horsepower to 30 horsepower, you can just live with 3 SKUs instead of 30 different SKUs.
I remember reading this book now, how much it got my sort of imagination going. But, you can just imagine, like, you just buy 4 of these tires with motors in them, and you literally can, like anyone can design an EV in their garage. You know what I mean? Like, this moves most of the complexity into this modular format where everything else is just like Legos, I just feel like it's going to open up an incredible amount of innovation once these things are ubiquitous, once these things are out there.
Funny you said that. There is, since we publicly came out a month and a half ago, at least 10% of people who are reaching out are exactly those folks who are making things in their garage. They're making very interesting 3-wheel, 4-wheel, 6-wheel concepts.
Yeah.
And so many of them want to upgrade it with just, hey, all I need is a wheel. I already have a 72-volt battery pack. I'm going to make it run.
Awesome. Okay, well, let's talk about the manufacturing bit. So one of the things I read in your materials is that conventional manufacturing is heavily tooled, and you are working toward a no-tool software-driven process, but I don't really know what that means. What does that mean, tooled and not tooled?
Very good question. So typically how people have done manufacturing is they make a manufacturing line, and they
Mm-hmm.
say, well, this manufacturing line, let's say, has 100,000 units per year capacity. And they invest in bunch of machines that are tailor built for the kind of product you're going to make on that line. So let's say you're making a 20 horsepower motor. There's a bunch of machines on that line which are quote unquote tools as well, that are tailored to that size of the motor that you're building.
And cannot be used to make a 40 horsepower motor.
Exactly. They cannot be used. So what happens in a setup like that is almost never day one you'll see that capacity. You'd start with, let's say, 10% capacity that's being used, or demand that matches that capacity, and then slowly you'll grow. And not only your ROI for the investment that you put in is going to take much longer.
Mm-hmm.
You also have these tools that are specific to that motor that also break down, and there's less fungibility around it.
Fewer manufacturers of those tools, presumably fewer people who can fix them, etc.
Correct. Super long lead time by those, because it's almost like it's artisan products. These are not large scale products. They are like 10 people in the world, or 5 companies in the world who do that, and they are in demand. Then you are lowest in the rung. So our vision was, we're focused right now on 1 to 30 horsepower motors. And our vision was, if we can make a manufacturing process such that on the same line, the exact same line, we can make a 1 horsepower motor, a 10 horsepower motor, a 30 horsepower motor across the board without changing the tooling based on the size of the motor that we are building, then that opens up the possibility of, when you make an investment in a line, you can make across multiple applications. You can have your capacity utilization much higher, which means your ROI for the line is much higher, number one. And number two, when you go from one geography where you had a manufacturing line to another geography, it's almost the same line that you can replicate, versus, oh, this other geography needs this other kind of motor, so I need to think about this from scratch.
Right.
So it allows for this repeatable automated setup that you can take from one territory to another territory and use the local supply chain of that area to be able to bring up manufacturing.
I see. And so if your line is cranking out 10 horsepower engines and you want to crank out some 30 horsepower engines, you don't have to replace tools. You just fiddle with software, basically.
That's right. Yeah.
And I sort of wonder, like, this seems obvious, right? Like, why wouldn't you do it this way? So why haven't people done it this way? Like, why are people building custom tools if it is possible to build a tool that's agnostic to size? Why haven't people been doing that?
I find that the best business ideas in the world are ones that seem very obvious on the surface, but have
Yes.
lots of complexity behind the scenes. And that's basically, David, what we have here. So the whole manufacturing process, the design of the stator and the rest of the motor, the way we integrate different parts together, the way we test them, and the testing infrastructure we built around it, all of these areas under one roof have been working towards making sure that such a line can exist. At the end of the day, we are a manufacturing company, so we got to get that right. And that's often the biggest challenge for hardware companies. So the team has been just focused on making that as simple as possible by making changes from a design and process standpoint.
And so you have one of these, you've built one of these, you have a line now that can crank out anywhere from 1 to 30 horsepower engines, or sorry, motors.
Yeah, we have a line in place already. The line is doing smaller volume right now because we are still making sure that it can produce at a sufficient scale, getting the integrity and the veracity of it right. And we're going to be scaling up manufacturing. Part of what we are going to do with the funding is scale up manufacturing. That's where a lot of our focus is, because we have a lot of demand. We need to get supply to the right point.
Yeah. So and when you say a lot of demand, like, is there a particular, like, as we say, these small motors are in all sorts of things. Is there a particular product category that is sort of like banging down your door that is most sort of hungry for these and most ready to go with them?
Yeah, on the small mobility front, we find two-wheelers, small delivery vehicles, as well as ag equipment.
Oh, yeah.
We see a lot of interest in that space. And then stationary products, we see fans and pumps. There's a lot of interest in that space. And what we are seeing more recently is around industrial automation as well, but certainly the first two.
How much can 30 horsepower do? Like, what is that? You're not going to get a car out of that. That's sort of like a tractor, like how big is 30 horsepower?
You'd be surprised with four wheels of 30 horsepower. You can actually get a decent small size car.
Really?
It's not going to be a super powerful car, but one that is fairly affordable and right sized for most folks that I find myself, hanging out with, especially as a city car.
Yeah.
But that's not necessarily the focus. If you look at a 20 horsepower or a 30 horsepower engine for that matter, you can easily run, a decent size or rather a small size tractor on it. You can run lawnmowers on it. You can run a lot of industrial automation, food processing plant to conveyor belts, pumps.
So you're covering the bulk of you think the motor market with 1 to 30? Like that hits most of the market?
That's where most of the commercial volume is. So there's residential customers as well, and that tends to be super high volume as a product. So think about the split AC unit that you may have inside your house. That's lower than 1 horsepower, where the volumes are super high, but it's a different class of products. And then you have much bigger than 30, 40, 50 horsepower, but their volumes tend to be much lower. It just tends to be a bigger unit.
Right. Yeah. So is there any plan to build like a, whatever, 30 to 60 horsepower line? Or are you just going to be content with the low end of the market for the time being?
No, we are a powertrain focused company. We will continue to work across all sizes of powertrains, but we got to have the crawl, walk, run where we have sufficient demand. As I said, we have to make sure our manufacturing line continues to perform at scale. Customers are happy with that. And then we can expand in both directions on the smaller as well as the bigger end.
Mm-hmm. So if I was going to build, like a modern luxury car, like a Tesla in the sort of Tesla market segment, and I wanted comparable performance, what is that horsepower in those motors, in those wheels?
Yeah, and Tesla produces many different cars, but think somewhere between 200 to 500 horsepower. And 400, 500 horsepower is like really luxury plaid type car. And I think 200 horsepower is a sweet spot for a lot of the medium duty cars that you'd find out there.
So when I say a 200 horsepower car, does that mean 450 horsepower motors?
That's right.
Like they're additive?
Exactly. And one of the things, we talked about rare earth free magnets, but our architecture is such that you could swap out the ferrite based magnets or the iron based magnets with rare earth magnets and significantly boost performance in the same system. So it's kind of rare earth agnostic, where with ferrite we are able to beat power density in the application classes that we are targeting, but with rare earth it could be a lot more, and we can easily use that to address the higher end of the market.
Oh, so you think when these things do end up in real full-size cars, they're probably going to be using the rare earth magnets?
Yeah, I think for trucks, it's possible it may continue to use ferrite magnets. But my guess is with cars, the kind of performance expectation people have for the larger cars, it may still need, it doesn't have to be rare earth magnets. It just needs to be stronger magnets than just purely ferrite magnets that are available today. And there are lots of chemistries that people are working on already. For us, that would be a drop-in replacement.
So chemistries that avoid the rare earth, avoid the supply chain.
That's right.
Struggles.
Yeah.
And this is like, I feel like I asked this once already, but I keep going back to it, which is like the whole world is electrifying. Certainly the biggest country in the world by population is the fastest electrifying country. And everybody, everywhere you look, is herding toward all sorts of cool electrical innovations and electrical widgets, and electrical systems and wires and just like the whole thing. And yet here, 50% of the world's electricity goes through these motors. And like somehow you're the only company who's like taking a go at making them better. It seems crazy. Like surely there are people in your wake. Surely this product category is going to get more active soon. Don't you think? Like,
Yep. No, the stationary world, which is where, the statistic of 50% of world's energy is passing through it, which is all the way from, commercial HVAC to food processing plants to pumping to residential applications. There have been lots of incremental innovations that have happened over the past, even like the last 20, 30 years. One of the biggest challenges that happens when new innovations appear is they tend to be lab projects and the manufacturability has not been 100% solved, or that becomes an afterthought. And in some cases, technologies are mature, but they are still very heavily dependent on rare earth. So while they have pushed things forward, there is a high dependency. So it's not that we're not claiming we are the only electric motor innovation out there. And in fact, I don't want that to be the case, because if the entire world needs to move forward, it can't be dependent on just one innovation alone. There needs to be many different innovations for different sorts of applications. It's just we have focused on material design, which is performance, and manufacturing process together, because we think the combo is needed to make something significantly forward.
Yeah, the manufacturability thing is really key. Over the years, I've come to pay a lot more attention to that, because like if you're looking into lithium ion batteries and you're trying to explain why they have such a lock on that category, it's partially chemistry, but mostly it's just they've manufactured the hell out of them for a lot of years and gotten really good at it. Like that alone is blocking a lot of other products out of that category. Just the manufacturing has been honed so well. So I have come to take that a lot more seriously. One more question about the limits of these things. There's a lot of debate about electrifying larger transport. There's a lot of debate about how far electricity can go, or whether you're going to eventually need some sort of combustible fuel, in ships, airplanes, etc. And most of that discussion has focused on the battery side of things. Like, can you get enough energy and power density into a battery to run a plane? But it occurs to me that like the motors are the other half of that story. Like they're they're the yin to the battery's yang. Are there improvements in electric motors, do you think, on the horizon sufficient that they could move up and start moving bigger, like planes?
Yep.
Are these going to help crack, if you can make motors good enough, are they going to help crack some of these hard to decarbonize sectors?
Yeah, absolutely. And, hidden within your question, two aspects. When you say bigger, sometimes that just means more kilowatts. Like, can you make megawatt size motors, or can you make tens of megawatt size motor? Like there's that. And then there is the power density part of it, because imagine a plane. Well, you don't want to carry a lot more load.
Yeah.
Every kg extra that the motor has is a kg of load that you are not able to carry in some sense. So I think both of those elements, I see a lot of innovations that I see in the market. But the fundamental problem there, I think right now, is less the innovation. It's the state of that market where there isn't enough things in production. And if you are a component manufacturer and you're supplying to a company where not enough things have gone in production,
right,
then you're sort of beholden by when the market will arrive, when will a consumer adopt.
Right.
And that's when your company, first, that company needs to be in business, and then you need to be in business. And that's the reason why we had the opportunity, in fact, to make for a bunch of eVTOL companies, make a high density motor.
Yeah.
And we believe in that, but just the market right now is not there. And so just as a component manufacturer,
there's just not enough demand to sort of justify scaled manufacturing, basically.
That's right.
It's kind of a chicken and egg thing there, though.
It is, but
I guess you need some policy.
I'll also say that personally, I'm not a electrification purist per se. So I'll explain what that means.
Oh, I know. This is a long running debate here on volts.
It's okay to think of hybrid as an option to begin with, where you
Yeah.
start using what's possible, what is at some level of scale. And scale is important from reducing cost also, because just because you manufacture something, but your ticket on that eVTOL is going to cost you $2,000 to go from San Jose to San Francisco, nobody's going to pay that. So what is the right combination, even from a hybrid standpoint? That, by the way, applies equally to cars, where there's a certain class of cars where hybrid makes a ton of sense for the market. It's okay to start there and then use that to seed to do something bigger and better and just completely electric when that opportunity exists.
Yeah, I guess I would just say I'm a big believer in the power of human ingenuity, and I just sort of think that once we start down this, like, we're going to be learning along the way, learning and learning, getting a little better, and then we'll do more, and then we'll learn more, and like, I think eventually on some glorious time horizon, we're going to get to all electric. Of course, the big question is when, but as you say, there's like plenty of room to get started. So just to review, the sort of innovations here are going to axial flux from radial flux, switching out the magnets using cheap, abundant iron-based magnets rather than rare earth magnets, and manufacturing agnosticism, I guess you would say, or software-driven manufacturing process. Are there, if we look in the future, fundamental advances still to be had in this space? Or is this one of those things where like electric motors have been around long enough that we're sort of like squeezing out efficiencies at the margins? Do you know what I mean? Like, are there big advances still to be had?
Well, 3 years ago, people didn't think so. And then the team here was able to put together some innovation to be able to get some major changes. So I'm absolutely a believer that advances in this space will continue to come. Part of what we want to do is, the top 10 universities in the world, even in the US, they didn't even have an electric motors focused program. So if we start showing to the world that, hey, businesses in this area are possible, they can be big, they can exist, and advances are needed, hopefully there's more focus, just like the battery world. Hopefully there's more talent that comes around it, and that leads to more ideas coming to it. So I would hate to say this is the last big innovation. I would love to see a lot more happen here. Ultimately, it's just about, at the simplest level, it's the highest amount of magnetic flux that you can generate with the least amount of material, and the simplest way to place that material in the right spot that can help you use different kind of magnet chemistries on top of it to be able to meet application specific demands. So I think there's a lot of opportunity in this space, and hopefully we continue to out innovate ourselves if possible.
All right. Sounds good. Well, this is really cool. One of the fun things about this job is just I discover whole new areas of interesting people doing interesting work that I didn't even know existed. So this is very, very fascinating. Just sort of dive into the motor question. And now it's like, now I'm like motor pilled. I look around, I'm seeing them everywhere I look. I'm like, oh yeah, there's another one. So thanks for walking us through this, and thanks for your work on this.
Thank you so much, David. Thanks for the opportunity to talk with you and share something with your listeners today.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.